to spend a ton more time discussing what kinetic energy is. It's energy in motion. So if an object is moving, it has a certain amount of, and the object is not moving, it has a certain amount of potential energy. Okay, well, does that have any potential energy due to gravity?
No.
What I was trying to get you to say is if it's not moving, how much kinetic energy does it have? Zero. Okay? So like when I do this and I lift it up, I'm putting work in to give it potential energy.
Oh, I hate that.
Okay? So I had to apply work. I converted work into potential energy. Okay? Now I'm taking potential energy and converting it into kinetic energy. Yes.
Why is pulling the marker up not kinetic?
It is.
Oh, okay.
Yeah.
Alright, okay, gotcha.
There is kinetic energy, but I'm also giving it kinetic work.
I remember you just like rough out my computer games where you built the roller coaster and it had to do with potential energy. I played it all the time.
Okay.
I was so bad.
So here you go. Kinetic energy is the energy due to the object's motion. So here are the two variables that depend on how much kinetic energy it has. What are the two variables?
Speed
Mass and
mass.
speed.
Okay. Speed and mass. Which one is more influential?
I would say
Mass.
Speed. Why would speed have a bigger impact on how much kinetic energy it has?
Velocity squared.
It's velocity squared.
There's literally about one.
So if I double the mass and I double the velocity, which is going to affect kinetic energy more? The velocity will. Okay?
That's a test question.
Now I was going to derive an equation for you, but we don't have time, so I'll just give it to you in a sec. Okay? What is kinetic energy's unit?
Mass
Joules. Now I want to show you how this becomes a joule.
Kilograms times meters.
A meter is, or a mass is going to be kilograms. And then a meter per second, that whole thing squared. So it's really a meter squared per second squared.
Wait, is that second squared?
No? Meter per second.
It's squared.
So a meter per second squared.
What is the velocity? Oh no, that's acceleration.
Yep. Whoa. Okay. So now I want to show you where we get a joule out of this. A Newton is a kilogram times a meter per second squared. So I can replace that with a Newton. What is left though?
A meter.
And that is a what?
A joule.
Wow.
But can you get
Science.
quadratic forms?
I just got pennies and clutch.
Okay. Because didn't I show you yesterday that a Newton times a meter is a joule?
Yeah.
Okay.
Talk about right
Wait, oh, Claire, I didn't get the kinetic
now.
energy.
It's in your notes.
No, it's not.
No?
One half.
Why did we never talk about radon?
Yeah. Do we actually need that?
Yeah, you'll need this a lot.
I
Yep.
thought the second one was part of it.
Which one?
They're the same thing. 1/2 m times.
They're the same thing, it's just that one's more.
This is in
No,
words.
I mean like the second one way under.
Oh, it's part of it, but I would, yeah.
It's not big of a problem.
Oh yeah, it's a noble gas.
Trust fund, I
Literally.
You get all the dip cans.
I mean, that's true.
That's what
That's because we get all.
All right. So here's the relationship between, remember how I said I took work to get potential energy and took work to get it to have kinetic energy? There's a relationship between the two here. The network is just the difference or the change in your kinetic energy. Okay? Now I can give you a much bigger equation, which I'm going to do here in a sec. So the net work done by all the forces acting on an object is equal to the change in the object's kinetic energy. We know that forces cause motion, right? So it makes sense that there's a relationship between force here as well. This is not what I want. Not what I want. Not what I want.
Oh wait, this is the way to class.
I told you that. Before I do this problem, we said that network equals the change in kinetic energy, yes? Okay? But we also know network equals a couple other things, right? So let's give you a nice, big, long equation that will
Is that gonna factor out so I don't actually?
Network equals net force times d cosine of theta, right? Isn't that what the work equation is?
Yes.
And we know net work also equals the change in kinetic energy.
Plug in force.
And we also know that kinetic energy is an equation, right?
1/2
Kinetic energy
velocity.
is 1/2 mv squared. The change in kinetic energy would be the final minus initial version of that.
Great.
Get that in. There it is.
That whole thing.
Yep.
Oh.
You don't need all the other equations if you have this one.
Yeah, well now I have all of them and the
I got
other
ones.
All of them and the other one.
I have this one and all the other ones.
I would put this in your note card and on your paper.
All you have to say is the change in kinetic energy equals that rate. Not include everything.
Well,
Oh my, what just happened?
sorry, I want to build.
Can you see now?
Because we said, guys, we said that net work equals the change in kinetic energy. But we also know net work equals this. And we also know change in kinetic energy equals this. So don't they all equal each other? Yes. Amen. This is really important because this is all of it in one. And so if you can do a problem and identify what variables you have, you can just find the equations you need and set them equal to each other.
Is it mass squared velocity squared? Velocity.
Just the velocity squared.
What was that? Well, that was the.
So should we put velocity squared in parentheses?
Units.
Or no?
If you want to.
It won't matter, will it? Well, no, is it, if you multiply.
The only way it would be mass squared is if I put parentheses around the mass and the velocity.
Yeah, but if you multiply the mass times the velocity and then square that, it's not going to give you an answer.
No.
Wait, so D is changing that.
Like
D, that's
Yeah.
that D.
Is displacement.
Yep.
Because when I say D, I think of density.
Alright, now let's do this problem here.
Wait, Kramer, why did you do final minus?
Because that's what, like change in velocity
Oh,
would be
okay.
V final minus V initial, so change in kinetic energy would be the kinetic energy final minus the kinetic energy
Why did
initial.
we know the change in kinetic energy, not just kinetic energy?
Because that's what equals the work. Kinetic energy doesn't just equal work, the change in kinetic energy is going to equal the work. Okay, so you cannot say that work equals kinetic energy. It equals the change in the kinetic energy. The difference between your initial and your final. Okay? So here we go, let's identify some labels here. We got a 7 kilogram bowling ball, move 3.0 meters per second. How fast must a 2.45 gram table tennis ball or a ping pong ball need to move in order to have the same kinetic energy?
Just turn it to kilograms.
Alright, so what do we know? Mass of the
A bowling
Bowling ball is 7 kilograms.
and then we also know the mass of the ping pong
And
ball.
the wrong thing.
So I gotta move that and turn it into what?
That means.
Auto.
It's easier than get my glasses out. 0.002. Wait, what is kilo?
What?
Is it 10 to the third?
Yeah.
10 to the third.
And we have velocity.
Okay, and then we have what?
V1 or V of
V
bowling ball for 3.
V net?
V of the bowling ball?
Or no? Oh no, it's initial because the final would be.
Well,
No, we don't know that.
you just need to differentiate between bowling ball and tennis ping pong ball.
Okay, it's just the velocity. It's not initial velocity, it's not final velocity, it's just velocity at one point.
It's kind of the net.
We're not using this equation.
It would be a.
Okay? And what do we have up here? 3?
I thought you said that would be the whole deal.
Not if you're just solving for kinetic energy.
Oh, so we're just doing it. No.
Yeah, this is the one, kinetic energy equation is the only one that's not involved in here, like just solving for kinetic
So we're
energy.
solving for kinetic energy and then.
Well, what it's saying is, it says, what would the speed have to be for their kinetic energies to be the same? So couldn't I say that kinetic energy of the bowling ball equals kinetic energy of the ping pong ball, and then I could just replace that with the variables of each. So 1/2 the mass of the bowling ball,
Which is 7.
B 3.5.
Let's go, I got it.
Isn't it M?
Oh, yeah, it's 7.
B1 equals M2.
is what?
M1 B1.
What about the half? Where did that come from? The square.
That's what you don't really.
So velocity of the bowling ball is this. So this here represents that, correct?
Really?
Equals,
Why did you set them equal to each other?
because they have to have equal the same kinetic energy. If they have the same kinetic energy, aren't they equal? You could have done this step by step, but I'm gonna do it in one step, knowing the fact that if they have the same kinetic energy, I can set them equal to each other. Right? Kinetic energy of the bowling ball better equal the kinetic energy of the ping pong ball based on what we're trying to accomplish in this problem.
I got it myself.
Okay?
And then you don't.
We do on the mass of the ping pong ball, 0.00245,
And then you don't on the wall.
and we're solving for V.
Oh, wait.
So you take the square last, right?
Your halves will cancel out.
Oh, I just realized.
Everyone else is up and down.
Okay.
Okay, so let's see, right, times 7. The follow-up question is really divided.
Did you do this reasonable?
Oh, wait, no, wait, didn't do it.
It's 160. Why did you take the half out?
Yeah, okay.
Divide by a half would cancel. Right?
Wait, so what's the actual issue?
I just simplified it all. I took and I divided this here, halves would cancel.
So you don't do anything with the half?
Well, you could, but if you take if you have a half on top and a half on bottom, don't they just cancel out?
I got a real big number.
Kramer half.
It should be, because guys, to get the ping pong ball with such a small mass to have the same kinetic energy as a bowling ball, it's gotta be cruising.
Which is why the second.
Right, like it is 4 miles an hour.
At least more
That's
than
way more than
like more than 2.
Like 6 billion? No, not 6 billion.
Not 6 billion.
Then it would
That's
not
not
be 160.
160 meters per second.
Question.
What?
The next part, is it reasonable?
Is it reasonable?
What kind of question is that?
I don't know.
It's relative. Kramer!
It's probably not.
I think it actually is.
It might be reasonable, but here's what I would think that maybe would make it unreasonable would be the fact that as you're going that fast, you have a significant amount of air resistance, correct? That's a force, correct? Is the ping pong ball going to be able to withstand that force? Probably not. It'll probably indent and break. Air resistance. If you're shooting a ping pong ball that fast, you got a lot of air resistance that is pushing on the ping pong ball that probably would crush the ping pong ball.
69.9 miles per hour. That is not that.
Well, it was in a vacuum. It's not.
69.9 miles per hour is way slower than that.
Yeah.
What was that? Yeah, he was just joking, I think.
Oh, I know, but I actually looked it up.
How fast is that in miles per
Oh,
hour?
I don't know, but the record is 69.9 miles per hour.
Oh, that's way fast. Yeah.
Yeah, probably. The fastest they've got a ping pong ball?
Yeah.
So that's the
Someone's actually
answer?
one.
Yeah.
Yeah, but there's probably
How,
some
that's
like
not the same kinetic.
lab equipment that you.
Let me show you. Let me prove to you that it's exactly the same kinetic energy. Someone take 1/2 times 7 times 3 squared. Tell me what that is. 31.5. Then someone else take 1/2 times 0.00245 times 160 squared.
I plug it in my calculator, I know it's true.
That's 357 miles per hour.
That's really fast.
Yeah.
Do you see how it's the same kinetic energy, Cheyenne?
Yeah.
I can run that.
Kramer!
What?
Like,
What?
if you have a lab
I
equipment.
forgot the decimal after the 160 to make it
Yeah.
such I was gonna
Yeah, good.
Kramer, so how come you chose to only take things from that equation up there?
I didn't use anything from up here. I use the kinetic energy
So why did you
equation.
give that to us?
Because of the next problem and
So-
other
We
problems.
have a final and initial.
Will we have every single thing in this problem needed for that?
Say that again?
Never mind, just do the problem.
Alright, this guy.
Oh no, I see initial.
Yep, we got some initial stuff here.
Oh, I love it.
Okay, on a frozen pond, a person kicks a sled, given an initial speed. How far does the sled move? Under a certain coefficient of friction. You're assuming that this is going to be until it what? Stops. Okay? So there are some things that we know. We know the mass.
We know mu k.
Okay, what is UK?
Point 10.
I'm so glad you say it.
Alright, what else do we know?
VIS. 2 point.
Since there's no other object here, I'm just going to say VI. Is that cool?
That's what. And then I'm assuming VF is 0.
Yep. Because it wants to know the distance traveled, so you would want where it stops, right? From the
So you need
beginning
change-
to where it stops.
Change in X. Or T if you want.
I'm going to use D in this case.
It's 0 because it's stuck.
Pretty slick.
Well, if I'm trying to figure out how far it'll travel until it stops,
So it would be 0 by the time it stops. Like
the
ball.
distance won't be, but the velocity will be when it stops. Yep. It's like if I push a sled, how far would it travel from when I initially pushed it to when it stopped? How far was that distance?
Oh, did we go back to like chapter 2 and do change in X?
No,
Okay.
we use that.
Oh, okay.
The big boy.
Alright, this is where it's a little bit difficult. But here, what variable up here are we solving for?
Peter.
D, so I'm probably going to need this. And what is the other part of this equation that I have variables for?
Yeah.
Velocity,
VI. So you can choose
So-
which one's.
Yes, that's the point of this equation.
Okay. Yeah, it does.
Because they're all equal to each other.
They all equal each other.
Oh. Yeah,
So if they all equal each other, doesn't this equal this, and 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 that?
So you're saying when this is each other, they actually.
Now, I'm going to eliminate something here because I know VF is 0. So I'm going to eliminate this portion here. Okay? Does everyone see what I'm doing on that?
No, I missed something. You're only eliminating.
Velocity final is 0, so you stop.
So I'm saying this equal to this, correct?
Yes.
Okay? I have a VF of 0, so that would totally nullify that portion of it. So this is my equation. I can solve for D. I'm just going to do that before I plug any numbers in. How about that?
What?
D equals -1/2. I don't need it.
You don't need it. Don't leave it. He only chose 2 things from that to say. Because it's all equal. That's what you said.
Divided by F
He
net.
was like, this is equal, this and this and that.
Cosine theta, but you don't.
You get
Yes.
acceleration.
But you only did.
Yes, because
So you don't
VF
need a
in this
cosine.
case is 0.
You just
So
say
if
that.
all those things were 0,
Yeah,
it's gonna be
guys, well, no.
Oh.
It's not.
Okay.
Okay, let's visualize what's going on here. We got a sled.
By 1
Okay? The motion is that direction, correct? Okay? We've got a particular force acting. What's the only force acting on this sled?
Gravity.
Okay, in parallel to the motion.
And the
But we're assuming that we're figuring it's right after I've shoved it, okay? So, I know M, I know VI, I don't know the net force. What is the only force that we said is acting in the parallel to the motion? So we have to figure out what friction is.
And then you use mu k.
Okay, stop. We need to find friction. But in order to find friction, we have to find Fn. In order to find Fn, we have to know the
Mass times 9.81.
Okay, so we know that Fg equals Fn because those are the only vertical forces. So Fn really is just Fg, or the weight.
Because 10 times 0.1.
Oh.
Times 9.81.
Yeah.
Alright, somebody give me what that equals.
998.1, I mean.
Uh,
And then when you multiply that by 0.1, it's 9.81. For the
it gives you 9.8.
0.1.
I see that. So this would be 98.1. Plug it in times 0.1. It's back to 9.81.
I hate that. That's great.
Okay, so Fn is 98.1. Plug Fn here times 0.1, which is the UK. Fk is just 9.81.
Is that net? Net is that?
That's the only force acting on it, so it is Fn.
Oh, because you're not assuming. Oh, it's after.
It's after you kick it. It's not assuming, you're not talking about the time frame while you're kicking it. It's from right after you kick it, here's the speed until it stops.
So F net and K are the same.
In this context, yes. Okay, now stop. Don't leave. This is very important. I'm going to plug this in. T equals -1/2. The mass is 10. The initial velocity is 2.2.
Square.
Okay? The net force we said was 9.81. Cosine of 180 degrees. Why?
Because it's a flat line.
Yeah, but doesn't.
No, because
We're going this direction. Remember, the angle is the difference between the motion and your force.
Oh, that's what that is?
Yes. Like, remember when I said if I move this way and I have a force this way, what's the angle? 90.
I said it was 0.
It gives you, cosine of 90 is 0. And so it gives you 0 work.
This goes at 182.
But if I'm going this way and my force is this way, that is 180 degrees. And 180 degrees isn't going to give you 0 work. It will give you negative work.
So F net equals.
Oh, it's slowing down.
Yes. Yes. It is slowing down, so you should have negative work.
I didn't realize that it's slowing down. It's negative.
What is cosine of 180?
It's negative 1. It's negative 1.
Yep. Yep. The answer is 2.5.
I want a big,
Wait,
big.
is it negative?
I'm making it here. Cosine of 180 is negative 1.
Is F net
Is what?
F net is
F is the net force, but in this case, there's only one force.
I didn't get it.
Friction.
What was the problem? Like yesterday,
Come in after school.
I was like, oh wait, stuff.
Class. So this class is. What?
Can I have some puffs?
That was finish the day.
Kramer, we should just leave our supply in here.
I had all the right.
Sure. I can't either confirm or deny the fact that I might need them all. No touching!
Okay, he took off points because I accidentally threw the asked the Cheetos instead of the line, which I totally did. But still, I had all my baggage.
I've only had.
I have got the penguin who's got his Cheetos.
Really? I have another. He looks like a.
Private. Status. Easy.
Are you a non-talking tourist now? Yeah. From Cozumel? That's what it's called? Mexico?
Actually, what's okay? That's my food thing. Literally go anywhere but your house. You can walk across the street. I don't know the tourist. Touring across the street. You don't even have a cat. Where's the guide?
How are we doing today?
Oh, I'll be your guide.
I'll walk there.
Are you gonna do your
What?
I would get better. Oh,
Alright! Cheese! Alright!
Next time, break it. I like
Break what?
They use a cell phone. What?
That's harsh.
Oh,
What do you mean?
Alright, open. I know this is like. It's like, that was a good Cheeto. Oh, wait, no. Okay, guys.